Hello, my friends. Ciao, ciao. So this is today. I'm recording this lecture to continue the exercise I had started during the last lecture. And just for context, we are in week 4, and this is the last lecture of this week. So this is lecture 2. So essentially, what I'm doing is to study this problem. This problem is continued from the last lecture. It's the analysis of a simple shear. Please be careful. I want you to notice the differences between these state of deformation and the state of deformation which is described in the assignment, okay? So take care, it's not really the same thing. I want you to notice why this is not the same thing, because you see, in the shear box of the assignment, the edges of these parallelepiped, they remain unaltered during the deformation, yes? So this is the case for the basis of this cube, but it's not the case for the height. You see, in doing the simple shear, the height, of course, remains the same, but this edge, this side, is altered, yes? So the edge, as you see, has a longer length. So this is not the case when you do the pure shear, so the two states of deformation are different. There is a question though, and the question is essentially very similar to the one that you see in the problem sheet in the assignment, which is to find the highest and lowest fiber stretches and their directions. We will address this problem by analyzing the eigenvalues and eigenvectors of the tensor C. Just for reference, I probably didn't stress it enough, but the tensor C has a specific name. It is called Cauchy Green, and in fact it's called Cauchy Green right stretch tensor. You don't. I probably last time I forgot to mention the name. The reason for which this is right is just to mention a little more. It's that, you know, we have seen that there is a polar decomposition. This is RU, but there is also the polar decomposition VR. Okay, and we have seen that C is equal to U squared, and instead we will define another object, and this object, I anticipate, it is called B. In fact, I did already talk about this tensor, and this B is nothing but V squared. So the reason for which C is called right is that in the polar decomposition, the stretch is located at the right. So there is a multiplication of two tensors, and the stretch appears here. So this is reason for which this takes the name of right stretch, okay? Right. And analogously, since B, this tensor here, which is rather related to the V, is instead appears at the left, then this is the reason for which this second tensor is instead called Cauchy Green, but this is left tensor. Okay, so we will discuss more properly later on, but what we're doing now is that we have already discovered that the eigenvalues possess properties of being maximum and minimum stretching of the fiber, and for this reason we want to find them, and we also want to find the unit vectors representing the directions in which these fibers have been deformed. On this I will go more in detail later on. So arrived at this point, we essentially have to find the eigenvalues. So the task is, so at this point, find the eigenvalues of C. Okay, so why do we find the eigenvalues of C? Well, this is the representation of C. Say in the Cartesian reference E1 E2, E3. And we know well, essentially, that when we represent the Cauchy-Green right stretch tensor in not the Cartesian reference, but instead the reference U1, U2, U3, then in this reference, C appears in a diagonal form, okay? So it's lambda 1 squared, it's his eigenvalue, lambda 2 squared, lambda 3 squared, okay? So, of course, then we understand that to find the eigenvalues of lambda, we essentially have to diagonalize the Cauchy-Green right stretch tensor. So, this is what I'm about to do in the next page. I want to copy again this tensor. So, question, find the eigenvalues and eigenvectors of C. Let me copy again this vector, this tensor. So this is equal to, well, we found it before, so this is equal to 1, k, 0, k, then 1 plus k squared, 0, 0, 0, and 1. Okay, so how do we impose the problem to find the eigenvalues and eigenvectors? Essentially, we want to find the couples lambda I squared, ui squared. Well, no, sorry, this is I made a mistake. The ui. So, well, this is simply the problem of eigenvalues, yes? So we have to solve the problem. First of all, the condition that C applied to the eigenvector ue gives you lambda I squared ui. So this is valid for 3 directions. So this is valid for I equal to 1, 2, and 3. And then there is the normalization condition because these eigenvectors have to be unit normals, yes? So essentially, the length of each of these eigenvectors has to be equal to 1. How do we solve this problem? We have already mentioned this. This is a classical problem in algebra. It is solved by imposing that the determinant of C minus, let me simply say, lambda squared I equal to 0, okay? And this takes the name of characteristic equation, or if you prefer, polynomial. Well, first of all, let me compute the matrix C minus lambda squared I. Well, this is equal to, well, you see, what I have to do is I have to take this matrix here and subtract lambda squared times the identity, which means lambda squared, there is here a matrix which is done by 1, 1, 1 and the rest 0, factoring lambda squared. So it means essentially that this matrix is equal to, well, let me just write it directly here. So we get 1 minus lambda squared k 0, k 1 plus k squared minus lambda squared, 0, 0, 0, and 1 minus lambda squared. Okay, so this is this matrix, and let me compute this determinant, which means I have to impose the determinant of this matrix equal to 0. Now, what is this determinant? Well, you see, we can expand the determinant of this matrix. For example, it is convenient to use this last line. So it would be the determinant of this point, it would be essentially this value times the determinant of this matrix, of the sub-matrix here. So essentially it becomes 1 minus lambda squared times the determinant of 1 minus lambda squared, k, 1 plus k squared minus lambda squared. Yes? And what is this equal to? well, this is equal to 1 minus lambda squared. And here I have, now, there is this times this minus k squared, right? So we have 1 minus lambda squared times 1 plus k squared minus lambda squared minus k squared. Okay, if you expand this expression, it is clear that this is, in fact, a sextic equation, but remember that the lambdas have to be positive, yes? So remember, each of these lambdas has to be positive. Why that? Well, you remember, lambda in general, it expresses a ratio between a deformed length and an undeformed length, yes? So clearly you cannot have negative solutions, because negative would mean that you have essentially annihilated matter. We're not getting into the real of antimatter here. We're describing the deformation of ordinary elastic matter. So for this reason, even though this equation is in fact a sextic equation, which means it's an equation which has a sixth degree, sorry for my accent, but in fact it is a cubic equation. So it means that from this equation we will get 3 roots. Now, the first of these roots is immediate, because you see from this expression we immediately obtain that the one of the first lambda is, let me call it lambda 3 for now, lambda 3 equal to 1, yes? So this is the first eigenvalue. You see, there is this bracket times this bracket equal to 0. So we immediately... Why did I set lambda 3 equal to 1? Well, this is somehow obvious, because this is in fact the stretch in the direction of E3. Why? Let me take the tensor C. In fact... If I take the tensor C and I apply the tensor C to the direction E3, you don't forget that E3 is precisely the direction in the thickness of the block. Yes? So there is E1, E2, and E3. So the block is being sheared in the direction of E2. Essentially, it's being deformed in this way. And you see, we clearly see that if I apply the tensor, so the block is being sheared in this direction, but in fact, if I apply C to the direction E3, if you look at the tensor this, when I apply to E3, which means essentially it's the unit vector, if you prefer I can write it more clearly, it would be 0, 0, 1. Right? When I do this is in fact equal to 1. Because you see, from this matrix here, when I apply to 1, we obtain 1. So this means that a first couple of eigenvalues and eigenvectors is in fact lambda 3 E3. So essentially, if you want, we can already write that the first couple of eigenvalue and eigenvector that we have found in the problem, oh sorry, just wanted to be more clear, this is U3, this is equal to precisely lambda, so equal to 1 and E3. Okay, so this is confirmed by the characteristic polynomial, but in a certain sense we could have spotted it immediately by direct inspection of that expression. Now what we have to do is we have to solve the rest to find the other two. So let me copy this expression to the following page. So continued from previous page, continued, find the other two, lambda 1, U1, and lambda 2, U2, okay? So let me write again the characteristic polynomial. Well, this is equal to, it's the rest of that equation, so it is 1 minus lambda squared times 1 plus k squared minus lambda squared minus k squared equal to 0. Okay, so let's expand a little bit the things. So we get 1 plus k squared minus lambda squared, and then there is minus lambda squared minus lambda squared k squared, and then plus lambda to the fourth minus k squared equal to 0. It's always very beautiful when things simplify, so this guy and this guy go away, and in fact there are objects which factor lambda squared, these and these, and then there are objects factoring lambda to the fourth power. Let's not forget there is something not factoring anything at all. Let's rewrite this expression more nicely. So this becomes lambda to the fourth, and then there will be minus lambda to the square, and here 2 plus k squared, and then plus 1 equal to 0. Now, of course, you can solve this equation, which is a quartic equation. Since the two roots have to be positive, you will find two solutions, two positive solutions. However, it is more convenient, to tell you the truth, to rewrite this equation as follows: lambda to the fourth minus the sum of the two roots plus the product of the two roots, where clearly the sum is equal to 2 plus k squared, and the product is equal to 1. So instead, this means that the two roots lambda 1 and lambda 2 squared, they are such that the sum of lambda 1 squared and lambda 2 squared is equal to 2 plus k squared, and the product lambda 1 squared lambda 2 squared is equal to 1. Now the latter essentially means that lambda 1 lambda 2 is equal to 1. So this is an interesting characterization. We will come back there. But essentially, if at this point we assume, for example, it's just an assumption, but you could do the other way around. For example, let's assume that for example, lambda 1 is higher than 1, higher or equal to 1, then this means that lambda 2 will be equal to 1 divided by lambda 1, which is lower than 1. So you see, this means that in this case, for example, we are attributing to lambda 1 the status of maximum stretch. So how do we find this? Well, we at this point replace this in this equation here, and we find that instead of writing lambda 2, we write 1 divided by lambda 1, so we get lambda 1 squared plus 1 divided by lambda 1 squared equal to 2 plus k squared. Okay? Now, to simplify this expression, we can write that lambda 1 squared plus 1 over lambda 1 squared, and then minus 2 is equal to k squared. And I want you to notice that this expression here, this left-hand side, is nothing but lambda 1 minus 1 over lambda 1 squared. So essentially, we were able to write this expression in this way, okay? So why is this an advantage? Because at this point, now, first of all, I want you to be careful on one thing. If lambda 1 is higher than 1, 1 over lambda 1 is lower than 1. So what is behind this, what is inside of this bracket is positive. K is certainly positive, so essentially we were able to simplify the equation that you see here. We can write it in a simplified form, and this simply becomes lambda 1 minus 1 over lambda 1 equal to k. Okay, so I realize it's a bit not completely straightforward. Of course, the most straightforward thing would have been to solve directly this equation. However, of course it's okay. It's just that if you do in this way, it is somehow the solution is more transparent. In fact, when you solve this equation, this is now a simple equation, it's just a second order equation. And when you solve this equation, you get that lambda 1 is equal to k divided by 2 plus the square root of 1 plus k squared divided by 4. And when instead of doing lambda 1, you replace in this expression lambda 2, then you obtain that lambda 2 will be equal to minus k divided by 2 plus the square root of 1 plus k squared divided by 4. Okay? Now, this actually concludes the search of the eigenvalues, because we know that lambda 3 is equal to 1, lambda 1 is equal to this value, and lambda 2 is equal to this value. Of course, we see immediately that since k is positive, we clearly see that this guy is bigger than this guy, yes? Please note that this guy is in any case positive, yes? I leave you to check. It's very easy to check by using the easy inequalities. It's easy to prove that. Try to prove it and think about it, but it is easy to prove that this quantity, if k is positive, is always going to be positive. But of course, this guy is lower than this. So we can essentially say that for any value of k, this lambda 1 is higher or equal of lambda 2, and for this reason we can claim that the maximum fiber stretch in the sheared block is lambda 1. This is the lowest, the least fiber stretch in terms of magnitude, of course. And instead, for what concerns the fiber which is along the depth of the block, this is lambda 3. Now there remains of course a question, because still there is a question which was the question that, a similar question, you find it in the problem sheet, but essentially it was the question for which we started. If we have the block in its reference configuration, in which direction we are shearing the block? I'm only drawing one face. In which directions do I find the fibers which are more stretched? Maybe this, maybe this, maybe this, maybe this. So, question is, what is the direction relative to the mostly stretched direction? Well, for doing that, we have to compute the eigenvalues. So we have to compute u1 and u2. I remind you that we have already found that u3 is coincident with e3. And this is what we are about to do. So let me find the eigenvalues. So it's still continued simple shear, and we want to find the eigenvectors u1 and u2. Now, in fact, it's not necessary to insist on 1 and 2. For what reason? Because clearly u1 and u2 are perpendicular. So, furthermore, they are also perpendicular to u3. So, in other words, how will they be done? Well, if this is the plane 1, 2, so let me say that this is the plane. This is direction E1 and this is direction E2. The two vectors U1 and U2 are simply two perpendicular vectors in this plane. So this will be, for example, U1, and it's a unit vectors which has an angle theta with respect to the horizontal. And obviously, since U2 is perpendicular, then the vector U2 will be like this, u2, and this angle will be again theta. So essentially you see that the problem of finding the eigenvectors in this problem boils down to find theta. Once we find theta, we can express the two components of u, yes? In fact, we can write that the vector u1 has components, for example, cosine theta along E1, sine theta along E2, and 0 along E3, right? So, let's impose the problem that defines the eigenvector. What is the problem that defines the eigenvector? Well, it's C applied to u1, for example, is equal to lambda 1 squared times u1. So let's do it. Let's just replace this together with the condition that the magnitude of u1 is equal to 1 determines the unit vector. But in fact, you see, we've already accomplished the condition that this is a unit vector. So this is already a unit vector. So okay, let's just rewrite this condition here. Well, let me recopy the tensor C. This is 1, k, 0, k, 1 plus k squared, 0, 0, 0, 1. So we want to apply these to u1, which means we have to write cos theta, sine theta, and 0. And then this is equal to lambda 1 squared, which is the vector, the eigenvalue I found in the previous page, times again cos theta, sine theta, and 0. Okay? So this is an equation. By solving this equation, we can solve this problem. Let's find the two equations coming from this problem here. So we get, of course, we get only two relevant. So let's do the first, for example. So here we are. Let me just write it like this. So the first, it would be the first line, because of course this is a vector. This vector has to be equal to this vector. So it is 1 times cos plus k times sine and 0. So we have cos theta plus k sine theta. This has to be equal to lambda 1 squared times cos theta. The second equation is k times cos plus 1 plus k squared sine, and this has to be equal to this. So let's write k cos theta plus 1 plus k squared sine theta equal to lambda 1 squared times sine theta. And the third equation is identically satisfied because it's simply 0 equals 0. How do we solve this problem? Well, in fact, we can do the following. We can multiply the first. To solve, you can adopt any technique you want. It's just this is more convenient. Factor the first equation times the sine theta, and factor the second equation times the cosine theta. So let's do it. I want to recopy these below. So this becomes, this becomes sine theta cos theta plus k sine squared of theta equal to lambda 1 squared cos theta sine theta. Multiply the second times the cos. So we have k times cos squared and then plus, let me expand this, so it becomes sine theta cos theta, and then there is plus k squared, again sine theta cos theta, and then equal to lambda 1 squared sine theta cos theta. And as you may expect, at this point I do the difference of these two equations. And when I do the difference, you see these cancels these. And so I obtain, so k times sine squared of theta minus k cos squared of theta minus k squared sine theta cos theta is equal to 0. In this expression, I can, since k is positive, then I can get rid of this, and I essentially obtain the following equation for theta. So we obtain that the angle theta that corresponds to the principal corresponds to the eigenvector u1 is equal to sine square theta minus cos square theta equal to k sine theta cos theta. Okay, so to solve this equation we can simply remember some trigonometric identity. In fact, we obtain that the sine the square of this quantity here, this is nothing but minus cos 2 theta. Okay, and on the other hand, the sine cosine, this is nothing but 1/2 of sine 2 theta. So to sum up, what we obtain is precisely the angle. So in particular, we specify this angle through the tangent. We obtain that the angle theta that corresponds to the angle to the eigenvector u1 is such that tangent of 2 theta is equal to minus 2 divided by k. Okay, so this is the direction, the slope of the first eigenvector u1. You could at this point say, but how can you be sure that this angle theta, this angle theta that characterizes u1, so don't forget that theta is the angle qualifying u1, does it really correspond to lambda 1? In fact, if you look at the derivation I did, I never used the value of lambda 1. Well, this is something that I leave as an exercise, so try to do by yourself this. Check it, okay? You have to find a way. In the notes, it's indicated the way that you could use. And it essentially passes from the fact that if you compute the value of lambda 1 from this expression, then you will find precisely the value that you have obtained we have obtained before, okay? So let me recap and interpret mechanically the findings we did. So finally, interpretation of the results. Well, what did we get? Essentially, we have obtained the following thing. Let me divide this screen into two parts, and I want to do it, you will see now why. For what concerns the vector c, which is the vector u squared, we were able to find the three couples of eigenvectors and eigenvalues, and we found that lambda 1 is equal to k divided by 2 plus square root of 1 plus k squared divided by 4, and lambda 2 is equal to minus k divided by 2 plus square root of 1 plus k squared divided by 4, and lambda 3 is equal to 1. And we have discovered, and let's contextualize in what configuration did we do this discover essentially. Well, you see, essentially the eigenvectors of C are also the eigenvectors of U. So the eigenvectors U1, U2, U3 that correspond to the eigenvalues lambda 1, lambda 2, lambda 3, they are eigenvectors of U. How do we interpret these? Now, these have to be interpreted in the reference configuration. And what does it mean? If I draw my imagined square, and this square is representing the undeformed configuration. The vectors u1, u2, u3 essentially live in this configuration. So we just found that, for example, u1 is a vector that has coordinates cos theta along e1 plus sine theta along e2, right? So this vector e1, u1 is this vector here. You see, it means that this vector has a certain angle, and this angle is defined by theta. And the other vector u2 is perpendicular to this and is related in this way. This doesn't help us much to tell us what are the fibers in the current configuration, because at this point we need to visualize what are the configurations, the stretched configurations in the current configuration. So when you analyze the eigenvectors of U, this essentially means that you're looking at the reference configuration. But since we want essentially to look at the current configuration, and this is the exercise that is contained in the assignment, you rather have to look not at C, but at B. And what is B? B is V squared. And if you remember, B is equal to F transpose. Now, when you compute the eigenvalues of B, as we said already, this will be the squared of these values, of course, but it will be still, lambda 1 will be still equal to chi2 plus square root of 1 plus k squared divided by 4. And likewise, lambda 2 is exactly equal to this, and also lambda 3 is again equal to this. So the eigenvalues are exactly the same. But, and this is, we don't do it, but I'm just anticipating what it means mechanically, you would find that the eigenvalues v1, v2, and v3 eigenvalues, eigenvectors of V and of B, of course, they live in the current configuration, okay? In the current configuration, which means that instead to visualize these new vectors here, I shouldn't draw the reference configuration, I have to draw the current configuration. And in fact, let me draw the reference configuration in this way. So this is just the reference configuration. Let me draw the current configuration in green. So this is the sheared block. Well, in this configuration now, the vectors the vectors V live here. So this is the current configuration. So if you want to visualize the vectors V, which means the directions in which the deformation is maximum and minimum, but in the current configuration, you actually should find the vectors V. Also, the vectors V will be similar. In fact, this is left as an exercise, and you are doing something similar also in the assignment. But the vector, for example, V1 will be something of the similar type. There will be an angle phi, E1, and then there will be an angle sine theta, E2. And if you at this point draw these vectors in this configuration, you discover something, and in particular you discover that the vector v1 is not, as one would expect, aligned with the diagonal. In other words, if this is the diagonal of this deformed parallelepiped, so if this is this diagonal and this angle, for example, is equal to alpha, then what you can find is that the angle corresponding to the most stretched fiber is not along alpha. Is not, in other words, this phi is not equal to alpha. This means that the mostly stretched configuration, mostly stretched fiber, So this angle phi here, and this would be the eigenvector v1, and its perpendicular would clearly be oriented in this way. Well, you would find that phi is not equal to alpha. This can be, you can do a quick calculation, and in fact I can anticipate that if you solve the problem to find, instead of finding the vectors u, essentially you find the vectors v, then you will immediately show that the angle alpha is essentially never equal to phi. And in particular, you can find that the while the tangent of 2 theta is equal to minus 2 over k, then you can find that the tangent of 2 phi is equal to 2 over k. So if you do a little calculation, and essentially you have to repeat all what we did for C, you repeat it for V. The only difference is that when you work in terms of C, or which also to say U, we work in the reference configuration. And when we work in terms of B, and that is to say in terms of V, we work in the current configuration. And what is important in the shearing problem is that in fact the mostly stretched fibers are not aligned with the diagonal, but are slightly offsetted. I just want to add, in conclusion of this exercise, I just want to remark that what we did in this lecture was essentially, in this lecture and in the past, was essentially to work in the reference configuration, and in this case in the current configuration. This I didn't do it, but please do it by yourself. So this is left as an exercise. This is do it. Okay. And just want to remark one thing, that normally you probably did already this with Michel, but I want to remark it, is that when we work in the reference configuration, you normally talk about Lagrangian description. And when you work instead on the current configuration, this is called Eulerian. Okay, so for this reason, the vector C and U refer to a Lagrangian description of the formation, and the vectors and the tensors B and V instead refer to a Eulerian description of the deformation. There is a final definition I want to give, and really very briefly, and it is the definition of a strain. And so what it is, the so-called Lagrangian strain. So it's something different than stretch, okay? So we have seen that essentially all the measures of deformation, they all pass through C or through B. But working in a Lagrangian formulation, which as we said previously, it means we're based in the reference configuration, all passes through C. We've seen that C defines the deformations of elongation, shearing, and also it controls the variations of volume, and so on. So everything passes through C. So if everything passes through C, when C is equal to the identity, then it means that the material is unstretched. So essentially, what does it mean? Well, you see, if C is equal to the identity, then also U is equal to the identity. And this means that the gradient of deformation, which normally is equal to R applied to U, well, this is simply equal to R. So essentially, the deformation in this case is simply a rotation. In other words, this means that you locally are not stretching anything. So since you may think, okay, if something is not deforming, I would like a quantity which is equal to 0 when I'm not deforming, you can introduce what is called the Lagrangian strain, and this is introduced in this way. It's denoted by E, and this is equal to 1/2 of C minus identity, okay? Which is to say 1/2 of F transpose F minus identity. So in this way, when the body is not stretched, then in this case the E is equal to 0. Okay? So this corresponds to the idea that we don't have deformations. I just keep these in some of the older versions of the notes. There were also, you can introduce also other units of deformation, but in fact it is not really important to introduce them, and with Michel we decided to skip these. It's just I wanted to highlight the existence of a Lagrangian strain, and in fact this has a name. It's also called the green, so for this reason it's appropriate to use the green, so green Lagrange strain. Okay, so really this concludes the application and the part on deformation. Of course, there may be more we could tell, but let me simply tell you that many of the things that we have discussed in this note, in this part of the deformation, need to be understood also by doing exercises. And with Harold already this week you did some exercises, and some more we will suggest them to you in the problem sheets. Okay, so that's all, and I think it concludes my part for what concerns these. It concludes my 2 weeks of lectures, and now I leave the ball to Michel for other 2 weeks, and so I will see each other in other 2 weeks, and I think I can anticipate that by next time you will study a very beautiful topic, and in fact on top of, exactly like we do in normal mechanics, in classical mechanics, after kinematics there are forces, but in this case you will learn that there is a new type of object that needs to be replaced, that needs to replace the concept of a force, which is the concept of stress, but it won't be stressful. Okay, so see you in 2 weeks, and enjoy with Michel. Bye bye.